between them. But before I start, one of the things I find when I talk to people about maths is just probably their eyes start to glaze over for sometimes, but actually people do find it quite interesting. But I find maybe about half of the audience always says, well, that's fascinating, but Mark, I haven't got a maths brain, so it doesn't work for me. And it's maybe because, people, they flunked their maths O level or whatever, didn't have very good maths teachers when they were young, and feel that it's not their thing. And the funny thing is, I did a maths degree, so I went to Oxford and I did a maths degree and I got a first. But all that really did is told me that I don't actually have a maths brain either. Because I got to the point where, yeah, I was able to do the undergraduate maths, but I got to a point where I saw what real mathematicians were capable of. And I got a glimmer of what, the human species, what their capability for abstract thought is. And that's kind of way up there. And I knew at that point that, my brain wasn't wired like that. I couldn't do maths like that. And so, I've got to a certain point, but I found that I don't have a maths brain either. But I think the take-home thing from that is that you don't have to have a brain wired up for it to appreciate it. So you can still make use of mathematical thinking at whatever level. And you can also, the great thing is that really clever people can solve problems, amazing, fascinating problems that people like you and me would never be able to solve. But we can learn about their solutions and be amazed by them, and get a richer appreciation for the world that we live in and the methods that we ring and the compositions that we ring. So my take home to start with would be, don't worry if you haven't got a maths brain, because that doesn't matter. You can still appreciate maths. So, right, with that out of the way, I'm going to share my screen. I've got a few slides for you. We've also got a few little practical things to look at. But let's see if you can see my first slide. So what I'm going to tell you today is that ringing is basically maths. So it's all about maths. Maths permeates ringing, and I'm going to try and show you how. But also, in terms of what maths is, I mean, maths isn't really about numbers or equations. Maths is about patterns. And it's about spotting patterns in the world or in abstract thoughts that we have. And actually, the key thing there is that we can link the patterns. So, if we spot the same pattern in one area that someone else is working on in a second area, and we can see it's the same, then we can link two apparently totally unrelated areas. And that is one of the ways by which knowledge advances very rapidly. So I'm going to give you an example, and this might not seem connected to ringing at all to start with, but I'll show you how it is. So a nice simple little example to start with. We'll talk about triangles. So a triangle, a very simple geometrical shape. I've got a picture there of a nice yellow triangle. It's an equilateral triangle, so it's same length edges. And the thing about an equilateral triangle is it's quite symmetrical. So for instance, if I label the points there so we can see what each point is, red, green, and blue, I can spin that rectangle round. I can spin that triangle round and rotate it, 120 degrees, and it will come back to the same place. And that's what symmetry means. It means an object is symmetrical if we can transform it in some way, either move it or rotate it or reflect it, mess around with it. And after we've messed with it, it still looks the same. That's symmetry. But as you can see, although it does look the same, the vertices, the points of that triangle have moved round. So the red point is now down at the bottom right, not at the top. And of course, we can repeat that, and we can find out there's actually three ways that we can rotate that equilateral triangle. And then if we rotate it a third time, it'll come back to the starting point. But that's not the only symmetry that a triangle has. So we can also reflect it, which you can think about as putting it like a mirror line down in it and almost like viewing it in a mirror. And if you look here, I've drawn a mirror line down the center of my triangle, right through the red vertex, right down through the middle. And if we flip it across that mirror line, you can see it's still the same triangle afterwards, but the blue and the green points have flipped. And of course, there are more axes of reflection, as we'd call it. There's more mirror lines. There's one through each point, each vertex. So there's 3 different ways that we can flip that triangle. And those are the symmetries of the triangle. Now, what's that got to do with anything else, you may ask? So I'm going to show you. And to do this, I'm going to stop sharing my screen, which, how do I do that? No, that's not right. No, pause share. Stop share. Right, and I'm going to show you my little workbench here. Okay, so once I figured out how to work all this kit, hopefully you will see on your screen my little workbench here, and I've got a triangle here, and I've instead of drawing in colored vertices, I've numbered them 1, 2, 3. And I'm going to show you rotations and reflections of that triangle, just like we did. Because I'm going to show you reflections, I need to flip that triangle over like that. And so what I've done is I've drawn on the other side, I've labeled the vertices in the same way. So you can see vertex number 2 here. On the other side, I've put a 2 to show you it's the same one. Same for 3 there, and 1. All right. So what I'm going to do is I'm going to do some reflections of this triangle. And first of all, I'm going to write down the order that the vertices are in now. So I'm going to start at the top and go 1, 2, 3 and write them down. And then what I'm going to do is I'm going to flip. I'm going to reflect my triangle along a mirror line that goes from this point through the middle of that line there, of that edge. So if I flip it, it looks like this. Right, so it's still the same triangle, but now the vertices are in a different order, and I'm going to write those down. They're 2, 1, 3. And you can try this at home, actually. It's very nice. You can cut out a nice bit of triangle out of a piece of paper, number the vertices, write it all down, see whether you get the same thing as me. And the next thing I'm going to do, so I reflected via that one last time. I'm now going to reflect by this line that comes down through the top. So if I do that, I grab it and reflect it like that. And then the triangle's in a different orientation. It still looks the same triangle, but the vertices are now in order 2, 3, 1. Okay, and I'm going to repeat that. So I'm going to flip on this mirror line here and write down at each stage the order I get, 3, 2, 1. Now I'm back to the top line there. Getting better at this. 3, 1, 2. And again, this one last time for these 2 axes. 1, 3, 2, and a final one for that axis there. And lo and behold, we're back to 1, 2, 3. And what have I written out here? Okay, no prizes. This is plain hunt on 3. So what we've shown there is we've shown the pattern of symmetries of a equilateral triangle map to a Bellringing method. They map to plain hunt on 3. So you can see how already mathematics is potentially useful in that we can, see patterns in ringing and we can map them to somewhere else, in this case, geometry. But that's maybe interesting, but what use can we put that to? Well, we'll maybe look at that next. But you might also be thinking, well, this is a bit of a con because it works for a triangle, it works for plain hunt on 3. But that's probably it, isn't it? That's as far as the analogy will stretch. But that's actually not the case. Hopefully you can see this here. This is a tetrahedron here. And I'll show you a net that you can cut out to make one of these for yourself. And as you can see, a tetrahedron, it's basically a triangle-shaped, triangle-based pyramid. And so it's got 4 points. And I've numbered them 1, 2, 3, 4. And again, you can play with the symmetries of a tetrahedron. It's got rotational symmetry. So I can rotate it round via an axis going through this top point and the middle face. And you can see how the points move around. there's another really weird axis of rotation. There's obviously rotational axis through the other points too. So line like that. And there's a really weird symmetry. There's a rotational axis that goes through the middle of one edge and out through the middle of the opposite edge. So kind of that orientation is the same as if I rotate 180 degrees to there. So that's really unexpected. And there are lots of lines of mirror symmetry too. And that's harder to do with a three-dimensional shape because you can't turn it inside out. So what I've done is I've made a second copy of my tetrahedron here, and I've made this to be the mirror image. Oops, there we go. The mirror image, as you can see, of that first one. And so with these two tetrahedrons, I can play with all the symmetries of a tetrahedron, and I can map out plane Bob minimus with that. But I'm not going to do that now because I'll probably make a mistake and screw it up. So that is an exercise for the watcher. Right, so I'm going to go back to my presentation. Let me just find my presentation once more. So that was triangles, and that we found was plane Hunt. And this is the map for a tetrahedron. So if you want to snapshot that screen later, I think Arthur says this will be on YouTube, so you can go back and watch it afterwards. And I'm sure you can find a tetrahedron net on the web if you really want to. But it's quite fun to play with and see whether you can get minimus methods out by rotating that shape around. There we are. It can produce the extent, all 24 changes on 4 bells. And the reason that ringing on 3 corresponds to the triangle, and ringing on 4 corresponds to the tetrahedron, and ringing on 5 will correspond to some other maybe hyperdimensional shape, is because they're both things are examples of groups, and that's the underlying pattern that describes both things. And the study of groups is called group theory, and that's why group theory is so important to ringing. And actually, there's names for these groups. So all 24 changes, the extent on 4 bells, and all the permutations between those, that's called the mathematical group S4. And it actually stands for the symmetric group with 4 elements, because it corresponds to the symmetries of things. It's quite a complicated group too. So one of the things we'll find out as we go through this is that actually the maths of ringing, I'm going to say interesting, not complicated, because complicated sounds a bit scary, but the maths of ringing, the group theory of ringing is really fascinating stuff. It's not simple. It's got all sorts of hidden structure. So I'm going to tell you what a group is. So this is the real maths. And actually, the good thing is about real maths is that it always starts off beautifully simple. If you can get somebody to explain it to you in a nice way, it's really simple. It's what mathematicians do with it afterwards that gets ever higher into the levels of the abstract. But the beginnings is beautiful. So you can think of a group as just a set of objects. Doesn't matter what they are, could be apples, could be bags of cement, could be numbers like we've got here, a group of objects, a set of objects, and some kind of operation that works on them. So the example I'm going to provide for you is of the integers as the set of things. And so that's basically all whole numbers, but the positive and the negative ones. And obviously they go up to positive infinity and they go down to negative infinity. And the operation that we're going to use is adding them up. And that makes a group. But to be a group, it's got to follow some rules. So I'll tell you what the rules are. So it's a set of things and an operation, but the operation's got to follow some rules. So here are the rules. And the first one we can summarize, there are 4 of them. First one we can summarize by saying it's like a closure thing. So when you add 2 numbers, add 2 integers, you've got to get another one. And so you can see that works for our nice little set here, because I can pick any numbers, you know, -3 and 5, and add them up, and I'll still get another whole number. So that kind of works. So that's good. And that's an important property of a group. Add 2 things in the group, they always come to something else in the group. The other property that's very important is the identity property. So there's got to be an element, and here it is, it's the number 0, which when you add it to anything else doesn't affect it. You know, it almost has no effect on it. So you can see, for instance, that if I told you I had a set which is, we start at 1 and it's the whole numbers 1 up, it doesn't include 0, and we're going to try adding them up. We've got the closure property there. You add any two positive numbers from 1 up and you'll get another larger positive number, but it's still in that set. But we've not got the identity. We've not got an object we can add to anything else and it stays the same. Got to have 0 in our set for that. The third property is elements have got to have inverses of each other. So if you pick any number in your set, any element in your set, there's got to be another one, and you add the two things together and you get back to the 0. So you've got to be able to reverse that operation. And again, you can see, even if we had the positive numbers and we added 0 in, you wouldn't have that reverse property, would you? Because if I said to you, let's pick the number 3, what can you add to it to get back to 0? Well, there's nothing if you've just got the positive numbers. So, but if you add the negative numbers in, then that works. So those are, 3 vital things for groups. And the final one is a kind of a subtle one. It's got to have the associativity property, which, if you remember your school maths, just means you don't need to bracket things up. The order you add things up doesn't matter. And that's all it is. And if you've got a set of things and an operation that works on them and it follows those rules, that is a group. And I suppose you might well ask, well, why those rules? Why are those rules the important one? And I don't really know the answer to that, except mathematicians have found those rules generate fantastic stuff that allow us to spot patterns throughout the world and solve problems with them. So that would be my answer to that. But maybe I suppose we've got some mathematicians in the audience, so maybe they can give a better answer later. One thing you might notice is missing from this list, and that's the commutative property. So if you're adding A to B, that doesn't have to be the same as adding B plus A. So the commutative property isn't necessary for a group. We do have that, obviously, with this group. This is a commutative group because 3 plus 4 is the same as 4 plus 3. But other groups, in particular ringing groups, they're not. So you can have groups where the order of a addition changes the answer. Right, so the other thing about this example group I've given you is it's one of infinite size. There's infinite numbers of whole numbers like this. So we can have a group that's infinite in size, but ringing groups aren't, because we've only got a finite number of bells to work on, well, most of the time. Otherwise, peals would take an infinite length of time. Even rounds would take an infinite length of time to ring, and that would be tedious, wouldn't it? So can you have groups on a finite number of objects? The answer is yes, you can. And here's a nice simple example of that. So it's adding numbers up, but again, you might remember this from school. It's a thing called clock arithmetic. And basically what happens is that if you add 2 numbers up and they get larger than your clock number, you just rotate the hand round and you go back to the smaller numbers. So if I added, for instance, 6 and 7, that makes 13, but that goes around to 1 o'clock. Yeah. So that's how clock arithmetic works. And that's actually a group as well. And we can just check. It's got the closure property. You add any 2 numbers in there and you get another number on the clock face, as long as you use the clock rule. We might think, well, there's no naught, so what's the identity? It's actually 12. You add 12 to anything else and you get back to the same number. So I add 4 p.m. to 12 p.m. It's 4 p.m. in the afternoon. Yeah, so the identity is there. And there are inverses too, so I can get back to that noon. So for instance, if I pick 3 and the inverse of 3 is 9, I add 3 and 9 and I get back to noon. And the associativity properties there, it doesn't matter here, 3, I could do the 3 plus 4 first and then the 4 plus 10, or I could add 4 plus 10 and then add that to 3. That wouldn't matter. So that is a group. And actually we can see that one of the interesting things about groups is they have some structure to them. Sometimes you can say, well, I can pick a subset of my objects and it still makes a group. It's a smaller group. So if you imagine you kind of graying out the odd numbers on this clock face, so you've only got the even numbers left, there's only 6 of them, that still makes a group because you've still got the identity element, the 12, You know, you add any two even numbers and you get an even number, so it's closed. So that's a subgroup. There's a little group hiding away inside the larger group. Bringing it back to ringing, clock arithmetic is a bit like the leads of a plain course. So I've written out here the leads of a plain course of plain Bob major here, and I've numbered them from 0 through to 6. Obviously, this last one is not really number 7. Remember, this is a round block, and we go back to the same point as we started. So that's back to row number, to lead head number 0. And you can see I can write that out on a little clock starting at 0. And that's just like clock arithmetic, you know. So you can imagine that plain Bob is going 0, 1, 2, 3, 4, 5, 6, and then back to 0. But if I thought about a method like Yorkshire, that steps through 2 at a time, doesn't it? That's this 5, 7, 3, 8, 2, 6, 4. That's the first lead head of Yorkshire. So to get the lead heads of Yorkshire, we like add on 2 each time. So we go from 0 to 2, and then to 4, and then to 6. And then if we add on 2, we go across 0 and to 1, and then 3 and 5, and then back home. So you can see the similarities between this clock arithmetic and things we have in ringing. And interesting thing here is there's no subgroups. You know, you can't pick out any of these 7 numbers and say, I'm just going to have 0 and 3. That doesn't make a group, or 0, 3, and 4. That doesn't make a group because, for instance, let's see, 4 add 4 is 1. 4 add 4 is 8, which goes to 1, and that's not in your subgroup. So the closure property isn't there. So this is a little clock group without any subgroups. But if you go up to 9 bell ringing, to 10 bell ringing, so you've got 9 leads in the plain course, there are subgroups. There's a subgroup of order 3, as we would call it. Every third lead head forms a little group, and that's why in royal methods you get methods with a 3 lead plain course. So you can see now how this internal structure of groups, the subgroups, actually has consequences in ringing. Just to say actually that groups appear absolutely everywhere. It's not just in the symmetries of geometrical shapes and in clock arithmetic that we've just looked at, and numbers, and in ringing. So the permutations of ringing form a group. There are all sorts of other places. So they turn up in the roots of equations. Like this is a quadratic equation, and whether you can solve a quadratic equation or even more complex equations like ones with x cubed and x to the power 4 in, it's group theory that gives you the answer to that. And they appear in physics, so in particle physics, at the heart of how particles that underpin atoms and other atomic elements, the rules that govern them are largely group theoretical. There's a picture of a famous woman mathematician here, Emmy Noether, famous a woman mathematician working in Germany before the Second World War that more people need to know about. She was kind of the woman who helped Einstein with his maths, because Einstein wasn't as good as maths as he was at physics. And she was a brilliant mathematician who really pushed forward abstract maths, so things beyond group theory, but she showed how symmetries are so important in physics and the theoretical underpinning of that. And the other thing that groups turn up in is public key cryptography, which obviously is securing all our communications these days in lockdown, and secures your internet banking and when you use Amazon and all of that. So the underlying maths for that, a lot of that is group theoretical. So this little structure that I've showed you with numbers and those 4 rules, that is amazingly useful, and it pops up all over the place. And it helps us solve problems. So this happens quite often, that in ringing we'll have a really hard problem that we can't solve, but some clever geometrician has solved it in the world of geometry. And we can then take that solution, and if we can map it back from the geometrical group to how that looks in ringing, then we can use that geometrical solution to apply to ringing. And there's theorems in group theory like Lagrange's theory, which is directly useful in ringing, and it tells us how we can compose peals in parts using subgroups. So if for instance, we wanted to find a peal which is a 7-bell peal, so the 5040 all changes on 7 bells. If we can find a subgroup of that group, the full S7, it's called, the full group over all 5040 changes. If we can find a subgroup and we can link that subgroup together with Bobson and sing the singles, then we may well be able to make a peal for it in parts, because Lagrange's theorem tells us there's a succession of other parts which will naturally be true. There can be no falseness. So it's very, very useful. And I'm just going to show you a little bit of history there, and then I'll show you one of the uses that one very clever ringing mathematician has put this sort of thing to. But just to say the history of this, because this is quite interesting. So group theory is, I mean, it's relatively recent. It wasn't anything known by the Arab mathematicians or the ancient Greeks. It was really developed by a number of people, largely in the 18th, well, the very late 18th and the early 19th centuries. People like French mathematicians like Lagrange, who I've touched on with his theorem, a young chap called Évariste Galois, who I studied at university, who was utterly brilliant. I really struggled to understand his theory. I eventually just got my head around it about 12 hours before my final exam, and it was due to start, which was just in the nick of a time and enabled me to get a few hours sleep. But you know, it was really hard just to understand it. But he created this brilliant theory, I think before the age of, he was about 19 years old, and he died in his early 20s in a duel of a gunshot wound, in a duel over a woman, I think. So he had very romantic lives, but very short life. But what he did was amazing, and he was particularly involved in the groups that underlie the solvability of those equations that I showed you. And actually, there was an Englishman too, this guy here on the right. He was actually the guy who pulled together all the ideas that separate mathematicians, particularly in France and Germany, were working on, and pulled them together and formalized them into the kind of the group theory that we know, with, you know, those 4 rules that I showed you. But despite all of this, so this is the history of group theory as mathematicians would know it, but actually Bellringers were using group theory, even though they didn't know it, much earlier than that, more than a century before. So if you read a Campanalogia, then you can see that people like Stedman, he understood group theory, and he was using group theoretical principles to try and find the extents on 5, for instance, and then extents on 6. And so it was really ringers who developed, I would argue, who developed group theory, and they developed group theory by inventing change ringing. And actually what we're finding now is that some of the ringing that was invented back then is now being recognized by mathematicians, and it's supplying 21st century mathematicians with some of the hardest problems they've ever seen. So it's amazing to think that these guys back in the 17th century, back in the time of the Restoration, inventing this pastime, this way of jumbling up the order of the bells up in the tower, the ideas they had there and the group theoretical foundation they put ringing on is now being recognized as really quite an amazing thing by modern mathematicians, well, some of them. I'm going to show you one last thing here, and that is how we practically apply knowledge from other fields to really hard ringing problems. And the other field we're going to look at is that of graph theory, which is quite closely related to group theory. And graph theory is nice because it's all about drawing graphs, which is lovely to look at. So it's a very, I mean, group theory can be very dry and arcane and very abstract, and graph theory is like, oh yeah, it's pictures. And this is a graph which you might figure out what it is. This is actually a graph of all the changes on 4. So there's all 24 rows here, and the arrows form kind of the edges of the graph. They're ways of getting between one row and the next if you apply certain place notation, so a certain kind of change. So that's kind of a graph of all the changes on 4 bells and one of the ways that you can link them. And so you can see that this looks useful, because if you didn't know, say, plain Bob minimus or any minimus methods, then you could look at this and maybe find a way of linking all those rows to form a true extent on 4. And indeed you can. So you can start here at 1, 2, 3, 4 down at the bottom left, and you can, apply, say, the change. Oh well, it's not precisely place stations that I've got here, but you can apply some kind of change to jump here and then there. Should have picked a better graph that had place stations rather than these are like rotations, aren't they? I've jumped from 1, 2, 3, 4 to 2, 3, 4, 1 here, but you can get the picture. You can draw an equivalent graph with just place notations, and then we can map out plain Bob minimus. So that's nice, and so we can find ways of finding the extent on a certain number of bells corresponds to drawing a path through a graph. But it's a certain kind of graph, so it is a path that visits all the, I'm going to call these nodes. So these are the nodes in the graph. They correspond to like rows or in Bellringing. And the edges between them are the transformations that link them. So to find an extent on 4 bells, I need to traverse this graph with a path that visits every node once and once only. So it visits every node once, so we're ringing all 24, and it visits each one once only, so the extent is true. And that special kind of graph is called a Hamiltonian cycle. That's the mathematician's name for it. And you can see how that could be useful on 4 bells, but the trouble is, as you get more bells, that graph gets bigger and bigger, and it starts to become, you can't do it by hand, and actually it starts to get really difficult for computers to do it. And by the time you get to 7 bells, you imagine there's so many ways of linking all the rows on 7 bells that you could fill the universe with computers and set them all off running, and you'd still never get an answer. But there are now very powerful algorithms that people in other areas of maths have created to try and find these Hamiltonian cycles. And they're algorithms with nice names like snakes and ladders and Concord. And the reason that there's been a huge research effort in trying to find these Hamiltonian cycles, or to try and solve equivalent problems, is because it's a really hot topic in maths and computers. Because Hamiltonian cycles and other problems like the traveling salesman problem you might have heard of, where it's a bit similar. You've got a graph with cities, the nodes are cities, and the salesman's got to travel between every city. He's got to visit them all, and he's got to do it in the minimum time. So he's got to use the shortest path. So it's quite similar, except you've got to go on the shortest path. And those problems are part of a group of problems which are really hard for computers to solve. We can't really solve them in any proper length of time. As you add, as you increase the size of the problem, the running time of the computer gets exponentially higher. And many of those problems actually, they underpin public key cryptography and keep that safe, because if it wasn't so hard, then you could solve the public key cryptography very rapidly, and you could break the communication. So it relies on the problem being hard and computers taking a long time to solve. But the trouble is, mathematicians don't know whether there is an algorithm out there that could solve these problems rapidly. So what they're looking for is an algorithm that could solve them in a time that's shorter than an exponential time. And if that algorithm exists, then it would tell us an awful lot about how the universe is constructed, but it would also have a huge impact on the whole of the world. I mean, for a start, it would mean all our public key cryptography we use now is useless. So it's a very important open question, and that means vast amounts of research time have been put into this over many years. And so we can leverage that to help solve ringing problems. If we can map ringing to this world of graphs and to these what are called NP-complete problems. And you might think, well, that looks very simple, doesn't it? Because here we are, we've drawn a graph, and I can, a graph of all the changes on 4, and I can use that to map through, say, plain Bob minimus. But there is a problem, and then I can apply these clever algorithms that still don't completely crack it. They're still in exponential running time, or they're not guaranteed to find the answer, but they're really clever. They really work well. The problem is that ringing is a bit more complicated than just a graph like that. Obviously, the graphs get larger and larger. Here, I've got a picture of a graph of 5 bells. So there's 120 nodes in that corresponding to each row on 5 bells. You can always see it's getting quite big. And we need to go much bigger than that if we want to get, solve peels of 7 bells. But here is the fundamental problem. Let's think about a really simple method like plain Bob minor, and supposing we wanted to make a graph of it. And here we go. Here's the first lead of plain Bob minor, this one on the left, starting from rounds and ending down here in just a plain lead, 1, 3, 5, 2, 6, 5. And so what we don't really want to do is have to have all the rows on 6 in our graph, because then that makes the graph very large. And actually, once you've got to 1, 2, 3, 4, 5, 6, you've got to carry on through this lead, haven't you? You've got no choice. If you're going to ring plain Bob, then you've got to go from this row to that row to the next and come out at the handstroke lead here. I mean, I've drawn a line here because this next row is really the start of the next lead, and actually that's where our graph would split. A plain lead would go to have an edge in the graph going to 1, 3, 5, 2, 6, 5. That's not quite right, is it? I've written that out wrong, haven't I? Yeah, it should be 1, 3, 5, 2, 6, 4, shouldn't it? Yes, yeah. Please do spot the errors in my presentation here. But yeah, but if there was a Bob called, then it would go to 1, 2, 3. What is it? 4, 6. No, 5, 6, 4. And so you'd have an edge in your graph going off to a start of another lead. But these first 12 changes from 1, 2, 3, 4, 5, 6 to 1, 3, 2, 5, 4, you can imagine we could get rid of those and just have one node in our graph that represents the whole lead. And that would be very nice and efficient. And it would represent kind of plain Bob. We could hop from lead head to lead head then. But the problem is there are 2 ways of ringing that lead, unfortunately, because we can ring it backwards. And to do that, we start at this handstroke lead end here and put it up at the top. So 1, 3, 2, 5, 4, 6, and we can ring it from there, and we get the same changes out in reverse. And that's a major problem because we've got to have both of those leads in our graph. But we can only ring one of them. Yeah, they're false against each other. But we could, we could have an extent on 6 bells with either of those, and that doesn't correspond to Hamiltonian cycle where we've got to visit all of the nodes once. So that's a problem for us. And you can see how different it is, because if we take this lead 1, 3, 2, 5, 4, 6, when we get to the end of it, we're back to rounds, but a Bob would take us somewhere else. It isn't taking us to the same place as a Bob from here, or a plane. And actually, you do use these backward leads in the standard composition of wrong, home, wrong. You ring part of the leads in reverse. So you need this problem property to ring an extent on 6. So the question is, well, that looks hopeless, doesn't it? We can't get that. That concept of having to have 2 different ways of ringing the same lead. We can't get that into a graph and hand it over to our mathematical friends to say, solve this for us with your clever Hamiltonian cycle or traveling salesman algorithms. But actually, maybe there is a way to do it. And this is where you can see sometimes, the relationship between one area of maths, ringing here, and another area, Hamiltonian cycle problems, isn't obvious. And you need to be able to figure out how to map between one and the other. And actually, there is a way of doing it. And I think we might have Andrew Johnson in the audience. What I'm going to show you is, I think it's his idea I'm going to show you. I think he'll correct me if I'm wrong, and he'll probably correct me afterwards if I'm showing this wrong. But this is his work as I understand it. So here's the basic problem. We've got these 2 leads, 2, 3, 4, 5, 6, starting from that lead head, and 3, 2, 5, 4, 6. We need both of them in our graph, but we can only ring one of them. So what we want to do is kind of map it to a one big fat node, like you can see on the right here, which has both of those leads in it. So it represents 2, 3, 4, 5, 6 and 3, 2, 5, 4, 6, both of those leads. So we just have to visit it once, and then we've got all of the rows within that. But we want to have the property that if we come into it one way, so we come into it the way that gives us the 2, 3, 4, 5, 6 lead head, then we can only go out of it kind of this way, the one that gives us the bobs and planes at the end of that way of working it. Conversely, if we come into this node down the red path here, which would come into a lead head of 3, 2, 5, 4, 6, we want to be forced to go out on the bobs and planes from the end of from the lead end that corresponds to that, and they go to separate places. The blue pass and the red passes, they go to to separate leads in the rest of the composition. And again, that's not a standard graph, having constraints like that, saying I've got a node here, but if you go in on this edge, you've got to come out that other edge. That's not part of a standard graph, and Hamiltonian cycle problems don't work on that, and your algorithms that your clever mathematicians have found won't work with that kind of thing. So you might think, well, we're just stuck. But lo and behold, there is a way of turning this kind of blue box I've got here with 2, 3, 4, 5, 6 and 3, 2, 5, 4, 6. There's a way of turning that into a little collection of nodes which work, and they give that property. So I'm going to try and show you that. So I'm going to swap back to my workbench and show you some magic. And this really is magic. I mean, if you didn't know that this could work, you probably would never look for it. Right, so stop share, and I'm going to go back to my other camera. So here is what the solution is. And basically, that big circle I had with those two leads in, that's what we've got here. This way in here, that's the the blue path that's that's entering from the top left. That's a plane coming in and a bob coming in from somewhere else in the larger graph. And here's the blue exits going out there. So that's a bob and a plane from the end of the lead that starts 2, 3, 4, 5, 6. And these are the equivalent external edges coming into the other lead head, the 3, 2, 5, 4, 6 one. And this is the end of that lead, and these are the edges going out. So these are the only way out to the rest of the graph. And this we can view as just like one node within the larger graph, but it's got some internal structure. We've put some other nodes within it, but they only connect to themselves. The only way in and out is via these paths. And then if you look at this, you will see this has the property that if you come in via the blue path, you have to go out via the blue path. There's only one way if you're going to visit all of the nodes, which you must do if you're going to find a true extent, if it's going to be a Hamiltonian cycle. Similarly, if you come in on the red path to a red node, you've got to go out via a red node, and that's forced, and there's no other way. And you might think, well, that can't be. But first of all, I will show you that the blue path works. So we can come in here to node 1, that's on the blue path, and we can go 1, 2, 3, 4, 5, 6, 7, 8, and they're all connected up. And so we can see obviously 1, 2, 3, 4, 5, 6, 7, 8, and then out via the blue. And we visited all 8 nodes, so that's good. So obviously there is a path that joins up the blue in and the blue out and visits everything in there. It's a bit harder to see for the red path. So if we come into 3 here, we can't just go 3, 4, 5, 6 and out there because we've left these nodes here. And actually, if you look at that, if we did do that, you'll see there's no way that we can connect all of the nodes up anymore. We came in, say, on 1 here. If we go to 2, we're stuck. The only way out is back to 1, which we've already visited, or onwards to 3, which we've already visited. So we're stuck. So we can't soak up all the rest of those nodes. But there is a way we can come in via 3. We can go 3, 2, 1, and then down to 5, across to 4, back up to 8, through to 7, and then to 6, and then out. So I'm just going to show you that again. 3, 2, 1, 5, 4, 8, 7, 6, and out. And we visited all 8 nodes, and we come in via the red, and we come out via the red. So those paths work, And that's not too hard to see. But the other magical property that this little node, this little subgraph has, is that's the only way of visiting all of these nodes. So you might think, well, that can't possibly be right. But watch, suppose I come in via 3 and I hoover up 2 and 1 and I vanish out via the wrong way. I've gone in by red and I've come out via blue. So I've used all of those. Now you think, well, I can still visit all the rest of these nodes. So let's try it. Let's come in via 6. Wow, we need to get 5 and 4. Then we've got to go to 8. But then we've got to leave. If we go to 7, we're stuck there. There's no way out. So if we go that way, we have come in and out, but we've left this node 7. We can never revisit. Conversely, if we went the other way, well, again, you get orphaned here. The only way out is to go 6, 7, 8, and that leaves 4 and 5 stuck. And actually, there's all sorts of other possibilities to look at here. But if you go through them all, there's no other way. The only way to visit all of the subnodes in this little subgraph that we've got is either via all the red path or all the blue path. Nothing else works. And so this little subgraph encapsulates, in some sense, the structure of the lead of plain Bob minor in a very abstract way. And it encapsulates the way we can bring it forward and backward in a way we can represent it in a graph that can be passed to a Hamiltonian cycle problem solver. And indeed, that's exactly the kind of thing that Andrew has done. I think he's spent years on this, trying all sorts of mathematical techniques, but he has applied this idea of these, he calls them in-out subgraphs, and it allows us to map a ringing method to a graph and get these problem solvers on it. And he's applied that to the problems of Erin and Stedman. So here's a picture of that of that in-out subgraph here. That's what I had on my piece of a paper here. Here's just one more picture showing how if you try and do it the wrong way, then you get stuck. You can't visit all the nodes. So it really works. Yeah, Andrew he's used other techniques too, but this is one of the techniques he's used to help find Bob's-only peels of Stedman, and he's still working on Erin. And Erin, even though we can push Erin triples into this world of graphs and NP-complete problems and get other mathematical algorithms to work on it, Erin triples, certainly the Bob's-only Erin triple problem is an example of a really hard problem that is harder than, for its size, is much harder than any problems mathematicians have found yet, which is an interesting thing in itself. But I think one day Andrew will solve it using these techniques, and he'll either find a peal of Erin triples, which is what we're all hoping for, or prove that there isn't one. So that's some of the techniques that that people at the cutting edge of ringing maths like Andrew are using to push our exercise and our ringing forward. Right, so that is the end of my talk, but I hope there were some interesting ideas in it for you, and I hope I haven't rambled on too long. I hope it made some kind of sense, and that's it. Thank you very much. Is that just a final picture of my hero Emmy, who I think needs to be more widely known as one of the greatest mathematicians and physicists that ever was.
Mark, thank you so much. That's absolutely fascinating. Thank you. We've actually just so people are aware, if you do have any questions, either type them in the chat box or raise your hand, and Mark will have a bit more work to do in the next sort of couple of minutes to hopefully answer those. Mark, whilst you were talking, Andrew actually typed into the chat box. I'll just read Andrew's comment, and I don't know if Andrew wants to say anything or whether you want to add anything to it. Andrew says, the idea of in-out subgraphs is that of Michael Haythorpe of Flinders University, South Australia. I found some much simpler ones for 3 in-out and 6 in-out nodes suitable for Erin triples and Stedman triples.
Yes, sorry, I didn't know that, but Michael, I knew Michael was working with Andrew on all of these problems. Yeah.
Super. And whilst we have Andrew in the audience, I don't know if Andrew wants to say anything. You're very welcome, Andrew,
I don't think much more. It's more that I explained the problem. They were a research group concerned about Hamiltonian cycles, and I explained the bell ringing connection to them, and they were interested. And he, with a bit of backwards and forwards, I managed to explain how the actual bell ringing side of things. And then he also come across these things called crown subgraphs, which were quite a complicated way of achieving this in-out property that we worked out was needed. And then having got that idea, then I just played around with some ideas of different graphs and got some simpler ones. I think they've now generalized them so that you can have any size of in-out subgraph, which might help, converting any sort of method type of problem into a Hamiltonian cycle problem. It might not be actually terribly useful, and once you start getting to spliced and things, it's really not very helpful. But you can see you can have a sort of a supernode for each possible row in a peel, and then you can have this magic subgraph for different ways it could be rung according to which method is being chosen at that particular moment. I think it might be more theoretically interesting rather than actually useful way.
Yeah, I think I'd say that's fascinating, actually, Andrew. And I think one of the things you said there, that's also the way maths works, isn't it? You've got people working on problems, and one person, finds just a way forward to push a little bit with it, but maybe their finding is it might work, but it's too complex, and then somebody refines it and moves it on to the next stage, and gradually you start to get to things that are useful and work.
Super. Thank you very much. Thank you, Andrew, as well, for your contributions there. Got a question from AJ Barnfield. Could you explain how to use heating and slow cooling to do some new 120s of Bob doubles?
Yes, so I think he's referring to, I had an article in the Christmas Ringing World about this, my use of simulated annealing to help with composition of spliced. And I guess that's a little bit similar to what Andrew's doing, not at the same level as his endeavors with the really hard problems of Erin. But again, what I was doing there, I was using what clever people have done in worlds outside of ringing. So the method of simulated annealing, that algorithm, which is inspired by the real process of physical annealing of metal, the heating up of metal and then the slow cooling down of metal to improve the crystalline structure of that metal. A group of researchers, I think at an IBM research laboratory, were inspired by that physical process to create this computer algorithm called the method of simulated annealing, and again they use that to work on these really hard problems, these what are called NP complete problems, which we can't really solve in sensible computer running time, but we can still explore them. And I adapted that algorithm in a similar way to maybe that Andrew's adapted things like the Hamiltonian cycle problems to ringing. And I've put that to use finding compositions of splice, and it's just magical. It's just an amazing thing. In the spliced, I haven't applied it to Bob doubles, AJ, but I've applied it to splice, and you basically feed in Bob calling. So you pick a Bob calling from maybe a single method peel, and then you randomize the methods between each pair of calls, and the randomization corresponds to heating, and the more heat you apply, the more you randomize them up, and then as you slowly cool them down, you randomize them less, and you start to become more concerned about the energy level of the crystals that are forming. And in a real metal, lower energy crystals correspond to larger, more perfect crystals. And if you can map, again, there's a mapping between one world and the other world. And in the physical world, the energy functions to do with the size of the crystals and the energy of the atomic lattice. In my ringing world, the energy function, I'm going to say, is to do with how good the composition is. So it's how much music it's got in, whether it's how false it is, how long it is, how much it mixes the methods up, whether it's all the work, all of those nice things I turn into an energy function. And as you cool down and randomize less and less, you start to worry about that energy more, and so you crystallize out these compositions that are better and better, and magically you get incredible stuff out of it. So that physical process really works in the field of ringing, and it's just flabbergasting. Yeah.
Super. Thank you for that. Mark, I have a question for you. I imagine when people sort of first begin to ring or teach ringing to others, maths, unless somebody has a particular interest in maths, it probably doesn't really feature very much in sort of teaching of ringing. And I wonder whether you thought we should be encouraging some level, some kind of appreciation of maths when we're teaching ringing, to new recruits, and if so, what kind of maths might be useful for us to do that with?
Yeah, I think the trouble is that if you call it maths, and you say ringing is maths, you put a lot of people off. I mean, obviously not the people who've come to listen to this talk, but there's probably at least 3/4 of the ringing population. If you tell them you have to learn about maths, they won't like that. And it's a bit similar to there's a lot of maths in method structure. For instance, because there's symmetry in method structure, and I'm fascinated by all of that. But if you try and talk to people about it in the pub, you get glazed eyes. But if you find the right way to put it, and for instance, if you can create a little puzzle that's based around method structure that's fun to solve, and people don't know they're learning about method structure and maths while they're doing the puzzle, then all of a sudden, oh, this is fun, and that's how methodocos work. So I think it's all about, I mean, the ideas, the underlying mathematical and logical ideas here are fascinating, and 99% of the ringing audience would probably find them fascinating. But I think people have got to realize that get over that barrier that maths is hard and maths is not fun, and just try and kind of, you mustn't be afraid of making a fool of yourself either, because not understanding things is also how scientists and mathematicians work. So a lot of people I talk to are frightened because they're going to get it wrong. It's like, well, if you're a mathematician, that's how you make progress, by getting things wrong. That's how you find out the new stuff. If you got it right all the time, you'd never find anything. So I think there's a barrier to public understanding of maths in ringing, and I hope talks like this will help to demystify it, and things like the methodoco. And it's one of my missions in life, because as I say, I haven't got a particularly mathematical brain beyond a certain level. But nevertheless, playing with it and playing with these ideas is fun, and not being worried about your own level of ability. I mean, I had some trepidation when I went to read Andrew's paper on this, because I thought, I'm not going to follow this. But I went and read it, and I picked it up, and there were some amazing ideas in it, and I'm glad. And so it's don't worry, have it, and just get stuck in, try and learn about these things, because they're amazing. They're just so incredible, some of these things, and also, of course, they will help you understand practical ringing. I've had several people come to me to said, now I've done your methodocos right to the end of your methodoco bit, I know a lot more about Bristol Royal now. It makes a lot more sense. I'm like, oh, good. So yeah, all that stuff is useful.
Thanks, Mark. Making mistakes tends to be the way I learn methods as well, I think. So
yeah, sure. Yeah. Don't be afraid of making a fool of yourself. It's.
Oh, I do that often, Mark. Don't worry.
Yeah.
Just whilst I'm waiting to see if there are any more questions that come up. A couple of comments in the chat box that I'll go through in just a minute. But just whilst I'm waiting to see if any more comments or questions come up, I'll just do a quick sell for the next couple of weeks. We're back to Wednesdays from next week. Obviously, normally we meet on a Wednesday. So next week, we're joined on the 3rd of February, joined by Gordon Breeze, who is going to talk about the impact of tower movement on bells, and of course on striking the bells. And the following Wednesday, the 10th of February, we have Linda Garton come to talk to us about ladies' pills and the impact of women on ringing. If you're interested, for those who aren't on the St Martin's Guild mailing list, if you're interested in hearing more about the Wednesday night talks, even though tonight's Tuesday night, but the Wednesday night talks that we normally have, just send me an email in the SMG CBR box, and I'll add you to our training talk mailing list. You won't get all of the stuff from the Guild, don't worry, but you'll just get the stuff around the talks. This is just a... Sorry, Mark.
I was going to say, there is one other question there that somebody asked, but I can answer that if you want.
Yeah, please.
somebody called AI, which is a little bit worrying, said, have you looked at juggling? I understand the theory behind juggling moves has the same sorts of structure as ringing. And the answer to that is I have a little bit. I did used to do some juggling, actually. Here we are. But again, I wasn't very good at that. But I have got a book. I wonder if I've got it nearby. I bought a book which the husband of an American ringer has written, which is all about the maths of juggling. And when I've read that, I'll be able to answer your question.
I think that question was by Alison. I think it's AL rather than a computer generated.
I was going to say,
question.
Right, okay. So the AI are asking excellent questions.
The AI getting very clever. Super. Yep. Thank you very much. Last opportunity for anyone to unmute themselves and ask any questions to Mark. I think there's a couple of comments coming through, Mark, in the chat box, thanking you for such an inspirational talk. So please make sure you have a look in the chat box for those. It just leaves me really to, somebody who definitely doesn't have a mathematical brain. I really enjoyed that talk, and on behalf of all of us here in the St Martin's Guild, thank you for such an accessible and fascinating talk, and the application of maths both to ringing and to the wider world. Actually, I think we found that really fascinating. So thank you very much.
Yeah, no problem. It was fun, and I hope you all enjoyed it.
Definitely. Super. Right, I'm going to stop the recording. Have a look in the chat box, and I wish everyone a good night. And thank
you.
And everyone for coming.